Now comes, in my opinion, the most useful part of all of this chemistry, and we're going to change it up quite a bit. We're looking now at what are called lithium enolates. So previously, we were always looking at different types of compounds where we're using actually fairly weak bases to deprotonate these carbonyl-containing protons. And if we go and take a closer look, we can see that the pKa of something like acetone is 19, the pKa of water is 14. That means that really this equilibrium definitely prefers to be on the side of the carbonyl compound. We're only making small amounts of this enolate at any given time. The concentration of the enolate is very small, but that highly reactive enolate is able to do productive reactions along the way. So now we're looking at what are called lithium enolates. These are going to be quite a bit different. Now we're going to use a new molecule. It is called LDA, lithium diisopropyl amide. It is very strong and it's very sterically hindered. So we already know that sodium amide is an extremely strong base. We always say its pKa of ammonia is 38. Lithium diisopropylamine has a pKa of 38, so it is even more basic than sodium amide. Additionally, when we look at this base, we see that we have these methyls, and it's good to keep in mind that each of these methyls have these hydrogens on them. Sometimes just drawing a line doesn't do justice to just how much space all these different atoms take up. So this means that we have this highly energetic, super reactive nitrogen anion in the middle that wants to take a proton from almost anything it sees, and it's surrounded by these very bulky methyl groups. So this has a number of consequences. The first is that it could do deprotonations very, very quickly. So it will not take very long, even at low temperatures, -78, to take this hydrogen from acetone. Now we have a nearly 20 pKa difference between acetone and diisopropylamine. So this reaction is effectively irreversible. So this has a number of consequences that are actually quite important for doing reactions with LDA and making enolates in this fashion. We're able to fully form the enolate and then do many new things with it. So as I mentioned before, with weak bases, this equilibrium is happening rapidly. It's going back and forth. So really, we're able to have sodium hydroxide, take this hydrogen, and make an enolate, such as the enolate shown. But since this is going forwards and backwards all the time, it potentially could also take the other hydrogen. And this would lead to an alternative enolate. Since these reactions are always going forwards and backwards, we can assume we are at equilibrium under these conditions. And that means that the thermodynamically more stable enolate will be the major enolate isomer in solution, with this other enolate being the minor component. So even though the major enolate is harder to deprotonate in some ways because it's more sterically shielded, right? It's harder to get access to this hydrogen than perhaps, say, this hydrogen over here. Sodium hydroxide is a fairly small small base, so it will be able to pick the one that gives the more stable product overall. This isn't going to be an exclusive product. It'll just be the major product. And the reaction will probably give most products deriving from this enolate. In contrast, LDA is very sensitive to the sterics of the system. And since we have this very big, bulky LDA that is protected by all of these methyls, it really cannot react with this more substituted hydrogen. It will exclusively go and deprotonate to give the kinetically favored enolate product. This is pretty much the exclusive product of the deprotonation. And since it is irreversible, because it's not going to go backwards, the hydrogen of diisopropyl will not be deprotonated again by an enolate. It's not nearly basic enough. So this is the intermediate that you're able to get out of the reaction and potentially use to do chemistry afterwards. So in reactions with LDA, what we're going to see is actually a two-step process where first we will deprotonate the carbonyl compound, then add in an electrophile. This will allow us to actually control things like crossed aldol reactions with complete selectivity only based on the order of addition. So if we wanted to react something like this cyclohexanone, we add LDA. Again, these are usually done at low temperature. So minus 78 is the temperature if you add dry ice to acetone, and it's very commonly used in organic chemistry. We make our lithium enolate. And after this forms, we can then, in a second step, add in our aldehyde. Note that since we don't have an equilibrium process, we don't have the same problem with elimination nearly as much. We can always control getting a hydroxy ketone product out of these reactions because we don't have these reversible deprotonations. We essentially make this alkoxide, add water to work it up, and there's no threat of heating it up too much to get the final elimination. So unless you want to add extra base after the initial addition, you do not need to worry about having the dehydration product at all. Similarly, we can have these lithium enolates react with other types of electrophiles beyond just simple carbonyl compounds. For instance, we could add LDA to this methyl cyclohexanone. Note that it makes, again, the enolate that we would expect, where it's towards the less substituted carbon. It will not take the hydrogen from a more sterically hindered environment. So even though, once again, we had two different types of hydrogens, it will take the more sterically accessible one. And now we can use this enolate and add in an alkyl halide to give a new methylated product. So this ends up being a very powerful way to make carbon-carbon bonds in organic synthesis. Alkylating lithium enolates that are generated from LDA is used all the time, both to do aldol reactions and also alkylation reactions. Note that there are some limitations on the alkylations. You need to have a primary alkyl, primary benzylic, primary allylic halide. Whenever you try to have something like a secondary or tertiary halide, these will undergo E2 elimination because this enolate is still fairly basic. So just so everyone is familiar with what I mean by a primary allylic halide, this would be something like allyl bromide. In a similar fashion, you can do the exact same sequence when you treat esters with LDA. So I'm just going to say R for now. So these are bulky isopropyl groups. So esters are less basic than something like a ketone. They're up more in the mid-20s generally. But still, we're going to have a huge pKa advantage by deprotonating the ester. Again, this will be an irreversible deprotonation. And ester enolates will be even more reactive than a ketone or aldehyde enolate. So this also coincides with them being less acidic. That means their conjugate base is less stabilized. It should be higher in energy. Note that we also now are having this electron donating oxygen next to this olefin. So we have this electron-rich enolate formed. And this will be able to do similar reactions with things like ethyl iodide. It'll have similar limitations on the types of halide electrophiles that you can use. And actually for this type of reaction, formally something like an aqueous workup is not really needed. Many times we will still add in an aqueous workup to get rid of some of the amide salts and lithium salts that develop along the way. But technically you would not need it to make the product. I would also note that many times you don't want to use too strong of an acid in some of these reactions. And so I've used this in the past, but I'll just mention it right now. Ammonium chloride aqueous, I think this might show up on the problem set. This is just a mild H3O plus source. So this will be used to prevent any potential ionization and elimination reactions of product alcohols that form in these reactions. So if you see ammonium chloride, view this as just a normal, slightly acidic aqueous workup. So now that we do have these sort of established processes to do aldol reactions, both at low temperature to give our hydroxycarbonyl compounds, or with heat to generate all the way to this double bond, now we can think about starting to combine this with other types of redox transformations we've learned in this class, whether it's reductions or oxidations, to now make some different types of products. So if we took this top molecule and we reacted it with sodium borohydride, we're going to be able to reduce this alcohol or this aldehyde to an alcohol, and we'd get now this 1,3-diol product. Alternatively, we could take lithium aluminum hydride. This will give us an allylic alcohol product. This would be after, of course, workup of some sort. And now things get even a bit more complicated by maybe looking at the types of other reduction reactions we can do. So if we were to directly hydrogenate this double bond, now we end up with a simple aldehyde. And hydrogen and nickel with high pressure are actually special conditions that can reduce carbonyl compounds and double bonds. And this gives us something that is almost even more unrecognizable from the starting material, where now it gets a little difficult to even tell this came from an aldol condensation reaction. So we're going to do some practice problems soon to illustrate these modes of reactivity. And so things we want to keep in mind is actually this 1-3 relationship of fragments, where if you have, say, two different R groups, if we have 1, 2, 3, this will be the relationship of where the aldehydes used to be. So this is 1, 2, 3, 1, 2, 3. We always have this beta hydrogen being the nucleophile, 1, 2, 3, and then the third atom away is what reacted.